Greetings to Dr. Nizam. We are from Section 3, Group 2. These are our group members. First is ARISSA ILYANA BINTI SAZALI. Second is me, Chung Ming. Third is GWEE, and fourth is ALYA ADRIANA binti Muhammad FAIZAL.
Assalamualaikum and hi, my name is ARISSA ILYANA binti SAZALI and my metric number is AF210072. Today, I will present about slab. For myself, I will choose the two-way simply supported slab. As you can see, this is my part that I used to calculate the slab. This is in TE/23 slab. Thing is I was to calculate the action. So the slab weight is 0.175, the thickness times with the concrete unit with concrete 25, and I got the 4.38 kN per meter square. Next, I got the design action with the formula 1.35 times GK plus 1.5 QK, that I got 11.28 kN per meter square. So for the analysis, the first one I do is this slab is one-way slab or two-way slab. So I calculate with Ly over Lx, then I got 1.4, and this is two-way slab. Then next I will check this, the case 1, 2, 3, or 4, or else. So if I check this, I get this slab is case 1. After that, I find the short span MSX1, MSX2, and the long span MSY1 and MSY2. So I get the MSX1 is 10.4 kN per meter, and the MSX2 is 14.1 kN per meter, and the long span MSY1 is 6.77 kN per meter, and the last one is MSY2 9.02 kN per meter. Next, for the main reinforcement, I check the effective depth first, the X and dy, and I got the X is 144 mm and the dy is 132 mm. So the first thing, I calculate the minimum and maximum reinforcement area to get the secondary bar, and I get for AS min is 187 mm square per meter. So I use the secondary bar is H12-300 is 377 mm square per meter. So the AS max is 7000 mm square per meter. Then I calculate the main reinforcement for short span. For the midspan first, I calculate the K, I got the 0.017 and it below K bar, so I used my K. Then I calculate the Z. The Z I got is 0.98D, so it under the 0.95D, so I used the 0.95D. And last one for the midspan AS is I got 191 mm square per meter, and I used the H12-300, that means 377 mm square per meter. I calculate the support for the main reinforcement. So my K I got 0.023, so I use the 0.023 because it's below the K bar 0.167. Then I calculate the Z, I got 0.98D again, so I use the 0.95D. Then I got the AS for the support 257 mm square per meter. Then I use the H12-300 for the top. So 377 mm square per meter. I use the same bar like past support and past the midspan. So then I calculate the long span and the midspan. I got K 0.1013, the Z 0.99D, but we use 0.95D. Then AS I got 135 mm square per meter. Again, I use the H13-300 for bottom. That I use this 377 mm square per meter. And last one for the support, I got the K 0.015 and the Z 0.99D, and also I used the 0.95D. And the last one AS, I got the 165 mm square per meter. Again, I used the H13-300 and no H12-300 for top, and the AS bar area is 377 mm square per meter. And for the shear span, I calculate VSX1 and VSX2, and the long span VSY1 and VSY2. Then I got the VSX1 to 24.2, the VSX2 is 24.2 also, and the long span VSY1 I got the 18.6 kN per meter. Also for the VSY2 I got the same 18.9 kN per meter. Then for the design shear force, I use VET equal to 24.2 kN per meter because it's the biggest. Then design shear resistance. First I calculate VRDC. Then before I got the VRDC, I need to search the K and rho 1. For the K, I got 2.818, but it below 2.0, so I need to use 2.0. Then I got the rho 1, I got the 0.0026, and then I can get the RDC. I inside the point into the formula, and I get 68.7 kilonewton. So for the Vmin, I get 78.08 kilonewton. So RDC big VED. So it's okay. Then for the deflection, the first thing I calculate, I find the percentage of required tension reinforcement. So I get the percentage is 0.0013. Then for the reference reinforcement ratio, I got 0.0055. So because of percentage of required tension reinforcement is less than reference reinforcement ratio, so I use equation 1. Then I calculate the L over D, get 185.3. For the modification factor for span less than 7 meter is equal to 1.00. Modification factor for steel area provided is equal to 1.98 is below than 1.5, so I need to use 1.5. And therefore, allowable span effective depth ratio L over D allow is equal to 277.92. So the actual span effective length is 34.7, is less than the L over D allow. So it's okay to my slab. Then I check the cracking. For the cracking, my thickness is 175 mm, below than 200 mm is okay. Then for the main bar, the max bar spacing 300 mm is less than S max slab, so okay. And then the secondary bar S max slab is more than max bar spacing. It's okay also. So the last slide, this is my detailing, as you can see.
Now is a subframe analysis, and these are our work distributions. And 1 level subframe by ARISSA, 2 level subframe by ALYA, 1 point plus continuous beam by Chung, and wind load and vertical load analysis by GWEE, which is me. This is a frame we are choosing to do the analysis. All of us are analyzing the subframe B with different methods. And the right you can see the clear dimension for the frame. To have a better view, this is a SketchUp 3D plan for our buildings, and the red circle part is a position where the subframe is. Basically, these are the method of the analysis, but except for the wind load and vertical load method. But the different method will have a different referral calculate point. So first, we have to find the action to obtain the fixed moment. And then we are doing the moment distribution, and finally we can calculate for the shear. And this step will generally repeated with different cases. For the wind load, before everything, we should have analysis how the wind will affect the structure of the building. So we have to calculate the wind load. And the wind pressure is calculated by considering the height of the building. Also, the shear and moment in the beam and column is calculated before we get in those 3 steps I mentioned just now. And last, we summarize all of our findings into diagram. And this is it for the frame. And to have a detailed calculation, please refer to our complete report.
Hi, my name is ADRIANA binti FAIZAL. My metric number is AF210060. So today I'm going to present about our group RCP project, which contain about column. So my part is corner column. So for the first step, I need to identify which one is the corner column. So after the identifying and listing all the descriptions, listing all the important things, I will start to calculate the actions on ground floor, first floor, second floor, third floor, roof, and everything else. So after calculating all the actions from ground floor, first floor, second floor, third floor, and roof, I need to identify the maximum action for all floors and also the minimum action for the floors to put it to calculate it for the axial force for the all floors. So I repeat the steps by calculating everything from the roof until to the ground floor column, so that I will know every load from the roof to the third floor, second floor, first floor, and ground floor. After that, I need to identify which this corner column is non-slender or slender. So I calculated the first step. I calculated describing all the column sizes, main beam and secondary beam. After that, I need to calculate the moment of inertia and the stiffness and the relative column thickness. After that, I calculated the effecting length of column of LOY and LOZ, and then I calculate the radius of gyration, and then I calculate the slenderness ratio, and then I calculated the slenderness limit, so that I can identify that this column, which is my part, it is a non-slender or slender. Then I identify that my corner column is non-slender. Both of them, x-axis and y-axis, are non-slender. So I listed all the important things for the design of non-slender band about major axis. So for the next step, I calculated the design moment for the corner column, which is I need to calculate the MED, MO2, and MO1, so that I can move to the further step, which is to calculate the main reinforcement for the corner column, which is I calculated to D2, and then I will calculate D2 over H, and then N over BH FCK, and then M over BH2 FCK, so that I can get the value from the design column chart. So that after that, I can know which bar that I can use for the main bar and also the secondary bar, and then for the for the links to. So for after I calculated, the main bar for the column is NH12, and for the secondary bar is 2H12, and for the spacing is H10 to 225. That's all from me for the column corner and column part. Thank you very much.
Next is about the foundation of the structure. All members are using PowerCAD with beam theory for the calculation. The selected foundation for each member is same as the selected column. I will be using my part, ground floor 3B, as an example for the explanation. The actual load and the moment applied on the foundation is calculated from the column design. The column size is designed to be 300 mm times 400 mm. Some assumption is made that the nominal cover for the foundation is 75 mm. Diameter of the reinforcement bar assumed to be 12 mm. Pre-stress reinforcement pile is 300 mm times 300 mm. Working load of the pile cap will be 600 kN, and the safety factor will be 1.40. To know the number of the piles required, the actual load is divided by the safety factor to know the service load, and the total of the service load and the self-weight of the pile cap is divided by the pile cap capacity, which is 600. And finally, we know that the number of required pile cap is 6. After that, we calculate the width, length, and depth of the foundation, and also the self-weight of the foundation. At the middle picture, you can see that this is the design column with 6 pile cap, and also the maximum service load per pile will be 506 kN, which is smaller than the working load of the pile cap, which is 600. Therefore, it is applicable. After that, we proceed with the analysis part. We first calculate the ultimate load per pile, which is 688 kN, and then we are able to know the maximum moment for XX section, which is 963 kN, and YY section 500 kN. Then we proceed with the main reinforcement calculation. First, we calculate the effective depth for Y and X. So the dx will be 919 mm and dy will be 907 mm. We first calculate the longitudinal bar first. The K value calculated will be 0.025, which is smaller than the K balance. Therefore, compression is not required. The AS required will be 2534 mm square per m. Therefore, we provide 24H12, which provide 2715 mm square, which is larger than the AS required. After that, we calculate the minimum and maximum reinforcement area. The minimum reinforcement area will be 207.6 mm and the maximum reinforcement area will be 60000 mm square per m. And the AS provided and also the AS required is in between this range, so it is okay to use. Next, we calculate the traverse bar. The traverse bar calculation is actually same with the longitudinal bar. We first calculate the K value first, which is 0.008, smaller than the K balance. Therefore, the compression is not required. Then, we calculate the AS required. The AS required will be 1334 mm square per m. Therefore, the bar provided will be 14H12, which the reinforcement area will be 1584 mm square, which is bigger than the AS required. Therefore, it is applicable. After that, we need to calculate the vertical shear of the foundation. There's 2 piles outside of the critical section. Therefore, the ultimate load per pile needs to be times 2, so that the shear force calculated will be 1375 kN. Then, we need to consider the shear reinforcement over the wall width of the pile cap. Therefore, after calculating, the VED will be 456 kN. After that, we need to calculate the design shear resistance. The VRD calculated is 502 kN and the Vmin will be 469 kN. By comparing with the results, the VRD is larger than the VED and therefore the shear is okay. Next, we need to calculate the punching shear. By using the formula, pile spacing is smaller than 3 omega pile, means that there's no punching shear check is necessary. However, we still do it for double checking. We can see that the maximum shear resistance calculated is 7713 kN, and it is bigger than the VED, which is 400 kN. Therefore, it is okay. Lastly is about the cracking of the foundation. By substituting the value into the formula as shown in the slide, we can know that the maximum bar spacing is all okay, and therefore this foundation can be used. As you can see, this is the detailing for the footing D/3. So the traverse bar will be using 24H12 as the reinforcement, and the longitudinal bar will be using 12H12 as a reinforcement. That's all from us. Thank you.